Now it is my pleasure to welcome online Zhenhao Hong.
Okay. Hello, everyone. Thank you for coming today. My name is Zhenhao Hong. I have been working on virtualization security, Windows kernel, and Hyper-V security research for many years. I was awarded the 2019 to 2020 MSRC Most Valuable Security Researchers, and I was also a Black Hat USA 2021 speaker. I also want to introduce my partner Ziming. He has been working on virtualization and kernel security for many years. He was the Windows project winner in 2021 Tianfu Cup, and he was awarded the Q2 and Q4 at Microsoft Most Valuable Security Researchers. In this section, Ziming made an indelible contribution. He first discovered this new attack surface, and we've been working on this attack surface. Here, I would like to express my thanks again to him. This section is divided into 6 parts. First of all, let's introduce the Hyper-V DirectX component architecture. In 2020, Hyper-V introduced a new feature of GPU-Paravirtualization, which is based on GPU virtualization technology. This technology is integrated into Windows Display Driver module, and all WDDM drivers above version 2.5 support GPU virtualization natively. However, new features mean new attack surfaces. This picture is the WDDM architecture diagram. Applications, such as 3D games, communicate with the DirectX graphic kernel subsystem by invoking the Direct 3D runtime component in user mode. The user mode display driver in the diagram is the private driver data of the GPU manufacturer, which will be used in the GPU kernel module driver. The diagram is the Hyper-V DirectX component architecture. The right side of the diagram is the simplified WDDM. The left side represents the child partition where the guest virtual machine is located. The DSG kernel Linux kernel module in the Linux virtual machine transmits data with the DirectX graphic kernel subsystem in the host machine through the VM bus component. The data flow of the WDDM is shown in the diagram. The application is the starting point. The application will invoke the APIs is exported in the runtime component. The runtime component may use the private data in the user mode driver, and then data reaches to DirectX graphic kernel subsystem and the DirectX graphic MMS. And finally, the data will reach the GPU driver. The data flow of Hyper-V component also starts from the application. The application sends data to the Linux kernel module, DSG kernel, through a set of IOCTLS exposed from the DEV DXG device file. The Linux DSG kernel driver module communicates with the DirectX graphic kernel subsystem in the host machine through the VM bus component, and the subsequent process is the same as WDDM. So, how to enable DirectX component in Hyper-V virtual machine configuration? You can use the add VM GPU partition adapter PowerShell command to add a virtual GPU to a specific virtual machine, and then use the get VM GPU partition adapter command to check the virtual GPU information. After we complete the virtual machine configuration, we can determine whether this component is enabled by checking the kernel log in the Linux virtual machine. For example, my Linux VM kernel version is 4.15. In the kernel log, there are 2 unknown GUIDs. There are virtual GPU DSGK channel GUID and global DSGK channel GUID. If the virtual machine is a Linux VM, only the WSL2 Linux kernel source code tree can natively support DirectX virtual device. But the good news is, DSG kernel driver for Linux is easy to compare and customization. The Linux driver for DirectX exposes the DSG device file to user mode Linux. The DSG device file exposes a set of IOCTL that closely mimic the native WDDM kernel service layer on Windows. Now, let's introduce the attack surface of Hyper-V DirectX component. First of all, let's introduce how the DirectX component is initialized in the Linux virtual machine. The DSG VMB channel init function invokes the VMBus open function to initialize a DSG cage channel. There are two functions here that will invoke the DSG VMBus channel init function. There are DSG global init global channel and the DSG adapter set VMBus. These two functions initialize a global DSGK channel and a virtual GPU DSGK channel, respectively. The DSG kernel Linux kernel module uses DSG VMB send sync message and the DSG VMB send async message to send DSG kernel commands to the host machine. And the DSG VMBus channel receive function is used to receive messages and commands from the host machine. By reading the WSL2 Linux kernel source code, you can see that there are many commands available here. The command message memory layout is as follows. All command messages consist of a header of size 0x18 and a message body. The header consists of 4 members. The channel type determines whether it is a virtual GPU channel or a global channel. And the command type determines which command to send. For example, DSG VMB send log2 function says DSGK VMB command log2 command to the host. In the command vGPU to host init2 function, you can see the DSGK VMB command log2 command is a virtual GPU channel command. And the DSGK VMB command log2 structure defines the format of the DSGK VMB command log2 command message. About data receiving in the host. If guest sends DSGK VMB command data to host, the VMBus component will invoke DSG host virtual GPU VMBus channel process packet, or the DSG host global VMBus channel process packet function according to the specific channel. And then VMBus process packet function determines whether to find the handler function corresponding to command type in the DSG host global VMBus command table VM to host table, or the DSG host virtual GPU VMBus command table vGPU to host table, according to the channel type. Finally, enter the specific handler function and continue the flow. The cast to VMBus command function is used to retrieve data from guest. For example, the value of D word at A1 offset 0x90 in the picture represents the length of the guest data. And the keyword at A1 offset 0x88 represents the pointer of the DSGK command message data. The VMBus complete function is used to send data to guest. The second parameter of this function is data buffer. The third parameter is the data buffer length. In this picture, VMBus complete packet will send the empty state value to the guest. Regarding the attack surface is located in the three driver files: DSG kernel, DSG MMS1, and the DSG MMS2. There are a total of 87 handler functions corresponding to commands, and each command also has a corresponding message structure. It is a huge attack surface. Now, I will further explain the attack surface of the above-mentioned Hyper-V DirectX component, using the four vulnerabilities of the Hyper-V DirectX components as examples. The first one is the CVE 2022-21918. It is a non-pointer reference vulnerability. The problem with this vulnerability occurs in the DSGK VMB command, signal sync object command. The root cause of this vulnerability is that the fifth parameter of the read SHI, signal sync object from CPU function, references a non-pointer. This picture is the stack batteries when this vulnerability is triggered. The read SHI, signal sync objects from CPU function, is shown in the picture. The fifth parameter assigns a value to V12, and then the V12, the reference calls non-pointer reference. The fifth parameter of the read SHI, signal sync objects from CPU function, is assigned by the fourth parameter of the read SH, signal sync objects from CPU function. The read SH signal sync objects from CPU function will be invoked by the signal synchronization object from CPU function. The fourth parameter of the read SCH signal sync objects from CPU function is the value of pfans values number of V5. In the signal synchronization object from CPU function, V5 is assigned by A1. A1 points to a D3D KMT, signal synchronization object from CPU structure. The memory layout of this structure is shown in the picture. In the DSG, host the virtual GPU VM bus signal sync object function. The pfans values number in the first parameter of the signal synchronization object from CPU function is assigned the value V24. As you can see, V24 will be 0 if V22 is less than V17. Now, we need to understand the memory layout of the DSGK VMB command, signal sync object command message. As shown in the picture, there are two members in the guest data VMBus signal sync object structure. The command member is a header of sex 0x18, and the sync object member is the message body of the DSGK VMB command, signal sync object structure tag. In this diagram, object handle array, context array, and the monitored fast value array are variable length arrays whose length and offset are controlled by object count and the context count. So, if V10 object count is 1, context count is 0, and the V16 buffer length is 0x3c. The V17 length of the monitored fast value array will be 8. V18 offset of monitored fast value array will be 0x3c. At the line 151 in the picture, V22 is equal to V16 subtract V18. So V22 is equal to 0, and V17 is equal to 8. Which means the condition that V22 is less than V17. So V24 will be assigned 0. It will cause a non-pointer reference in the following process. The POC code is divided into two parts. The first part is used to create a sync handle, and the second part is used to send the DSGK VNB command, signal sync object command. Setting the members in the signal sync object structure as shown in the picture will trigger this vulnerability. The next one is CVE 2021-43219. It also a non-pointer reference vulnerability. The problem with this vulnerability occurs in the DSGK VNB command, submit command. This picture is the stack backtrace when this vulnerability is triggered. In the DSGK submit command internal function, the second parameter of the DSG context handle West BLTSTUB function is V37% history token. And the value of V37% history token can be controlled by the guest machine. In the DSG context, handle West BLTSTUB function, if A2% history token is less than 0, the code flow will enter this branch and invoke cwin32k log function. The first parameter of the cwin32k log function is a cwin32k log structure pointer. When this vulnerability is triggered, some members of the cwin32k log structure are illegal now, finally cost the BSOD. The picture shows the POC code. The first part is the create context handle. The second part sends the submit command message. Setting the members in the submit CMD structure as shown in the picture will trigger this vulnerability. In the POC code, the present history token is less than 0. The following is the debugging process. First, set a breakpoint at DSGK submit command internal offset 0x89D. When debug executes the breakpoint, check the second parameter percent history token. It is less than 0 now. Single-step tracing until cwin32k log is invoked and display the memory pointed to by the first parameter. You can see that many members in the cwin32k log structure are not initialized. So these uninitialized values are referenced in the cwin32k log function and cause the crash. The next one is the CVE 2022-21912. It is an arbitrary address read vulnerability. The problem with this vulnerability occurs in the DSG VNB command wait for sync object from GPU command. This picture is the stack backtrace. The memory layout of the DSGK VNB command wait for sync object from GPU command message is shown in the diagram. In the DSG host virtual GPU VM bus wait for sync object from GPU function. If like seen, fence object is 1, sync GPU fence value will be assigned to DST pfence value, and the V23 will be assigned to 0. The fourth parameter of the DSGK wait for synchronization object from GPU internal function is 0 now. At the red mark, because V5 is equal to 0, source pfence value will be assigned to V5. And the source pfence value can be controlled by guest machine. In the following code flow, V5 will be used as the third parameter of the wait for synchronization object from GPU function. In the wait for synchronization object from GPU function, V10 is equal to A3. At the red mark, V10 is dereferenced directly and cause arbitrary address read. The POC code is divided into three parts. The first part is to create a context handle. The second part is to create a sync handle. The third part sends the wait for sync object from GPU command message. Setting the members as shown in the picture will trigger this vulnerability and read data from address 0x4144141. The following is the debugging process. Let's set the breakpoint at a wait for synchronization object from GPU offset 0x1945. When debug executes the breakpoint, check the ISR register, and the value of ISR is 414141. We can control this register from a guest machine. The last one vulnerability is the CVE 2022-21898. It is an arbitrary address write vulnerability. The problem with this vulnerability occurs in the DSGK VMB command submit will percent history token command. This picture is the stack backtrace. The memory layout of the DSGK VMB command submit will percent history token command message showing in the diagram. In the DSG host virtual GPU VM bus. VM bus submit will percent history token function. Percent unknown for is used as the seventh parameter of the DSG adapter. Submit percent history token from VM function. In the DSG adapter, submit percent history token from VM function. A7 unknown for is written to the address of V29 offset 0x300, and then with SCH submit command contested this function will be invoked. V29 is the first parameter of this function, as shown in the picture. The second parameter of the with SHI redirected flip with on-sync object function is the first parameter of the with SCH submit command contest this function. In this picture, the second parameter of with SHI acquire private data reference function is the first parameter of with SHI redirected flip with on sync object function add 0x238. In with SHI acquire private data reference function, when v2 is 0, the keyword value at the address of A2 offset 0xC8 will be written to v4. The value of v2 is v6 in the the value of A2 is v6 in the with SHI redirected flip with on sync object function at 0x238. 0x238 at 0xC8 is equal to 0x300. So the keyword value at the address of A2 offset 0xC8 is the A7 unknown for. In the DSG adapter submit percent history token from VM function. The following is the code flow. Adding 1 to the address of v4 offset 0xC cause arbitrary address write, since v4 is equal to unknown for. The first part of POC code is a create sync handle. The second part sends the DSGK VMB command submit will percent history token command message. Setting the members as shown in the picture will trigger this vulnerability. The following is the debugging process. As shown in the picture, when this vulnerability is triggered, it will finally cause arbitrary address write. Let's talk about fuzz. Why fuzz is necessary? First, Hyper-V DirectX components has a large quantity of codes. Second, there are 87 commands and their corresponding structures. Multi-team members in a specific structure can be very effective. And many commands depend on context, such as some commands depend on device handle or location handle. Meanwhile, the properties of the handle, such as the properties of the allocation handle, will also affect the commands that refer to it below. In this case, it is more efficient to use fuzz. and above vulnerabilities were all discovered by Fuzz. A simple Fuzz architecture as shown in the picture. The fuzzer is deployed in the guest machine. The major function of the driver part of the fuzzer is the agent layer, which is used to send the DSG kernel command data obtained from the user mode program to the host DirectX component, and receive data from host DirectX component and return data to user mode program. The major functions of the userland part of the fuzzer are send mutated DSG kernel command data and receive data returned from the kernel module, such as the return data of create allocation command. The userland fuzzer contains two core modules. The data send and the receive module is used to communicate with the driver, and harness mode module is used to harness generate. For example, by mutating the members of the DSGK VMB command signal sync object structure in the DSGK VMB command signal sync object command message, the above-mentioned non-pointer reference vulnerability was discovered. Now, as conclusion, there are some of my opinions on Hyper-V DirectX attack surface security research. This attack surface is still worth researching because the Hyper-V DirectX components has a large attack surface and is still being updated so far. About application scenarios, Hyper-V DirectX component application scenarios include WDDM, Windows Sandbox, and Holiness 2 emulator. Since virtual machines can natively support DirectX, online 3D gaming may become possible in the future, I guess. About Bounty, unfortunately, MSFC thinks Hyper-V DirectX is out of scope for Hyper-V Bounty program, but also thanks MSFC for the patient communication. The three takeaways included in my presentation are as follows. First, I introduced the Hyper-V DirectX component architecture overview and how to enable Hyper-V DirectX component in Hyper-V virtual machine configuration. Third, introduce the attack surface of Hyper-V DirectX component and how to find vulnerabilities in this attack surface through fuzzing. Third, disclose the internal details of the 4 Hyper-V DirectX components vulnerabilities, providing reference for finding vulnerabilities in this new attack surface. Thank you for listening.